My talk will be about global neighborhood completeness of the Lindstrom probability logic extended with non-well-founded derivations. Let me briefly recall Lindstrom probability logic. GLT is a bimodal logic which is given by the following Hilbert-style axiomatization. Tautologies of classical propositional logic, normality for both boxes. I will write box and box times. Box and box times. Lopes axiom. And axioms that describe connections between these two modalities. We have three such axioms. And inference rules, modus ponens, and necessitation rule. Okay.
Only for this type of blocks.
We have this monotonicity axiom, so the second rule is derivable. This system describes properties of probability predicates. It means it's sounded complete with respect to its arithmetical interpretation, where the first box can be understood as the standard probability predicate of Peano arithmetic, and the second box corresponds to Peano arithmetic, for example, extended with so-called Parikh rule, which looks like this. If it's probable that phi is probable, then phi. So these two systems have the same set of axioms, but it's not probable in Peano arithmetic. So Peano arithmetic only knows that these two model connectives relate to each other in this, like this. And I will discuss neighborhood semantics, global neighborhood completeness of this logic, and this is similar to a situation for the Gödel probability logic, which is just a unimodal fragment of this system. And I wanted to clarify how we can generalize approaches for Gödel probability logic to a bimodal case, and byproduct of this this investigation, in addition, is sequence calculus for the Lindstrom probability logic, non-well-founded sequence calculus. Okay, now I remind neighborhood semantics. Let me, where is, let me say that transitivity is probable in this system for both model connectives. The Lopes axiom for the second connective is also probable. So I haven't written them. So only axioms that describe connections between these two model connectors remain. Neighborhood frame, unimodal neighborhood frame is a set X together with a mapping acting on subsets, on the set of subsets of X. And this neighborhood frame is called a Sakia frame if all axioms of the Gödel probability logic are satisfied. That is, we evaluate propositional connectives as subsets of this set X. Model Boolean connectives correspond to Boolean operations on subsets, and the model connective box is interpreted as this mapping. So a Sakia frame is a frame where all axioms of GL are valid. And we will also consider a bimodal neighborhood frame, and all definitions for this case are similar. Just to remind, a model is a frame together with evaluation, where evaluation is a mapping from formulas to subsets of X. And I will write that A formula A is true at A world X of this model if the value of A if X belongs to the value of A. Okay, it's just standard definitions. Now I will define non-well-founded derivations in the Gödel probability the Lindstrom probability logic, and then show you corresponding consequence relations over neighborhood frames. Non-well-founded derivation is a possibly infinite tree of formulas constructed according to inference rules modus ponens and necessitation, such that any infinite branch in this derivation must contain infinitely many applications of the necessitation rule. So it's non-well-founded derivation. I will write gamma turnstile A with subscript G for global, if there is a non-well-founded derivation with the root marked by this formula A, where all leaves which are not marked by axioms of the Lindstrom probability logic are marked by some formulas from gamma. So is a non-well-founded derivation where all assumption leaves are marked by some formulas from gamma. There is also the standard local derivability relation in this logic. I will write A is locally derivable from gamma. That is, A is derivable by a finite proof using only the rule modus ponens and theorems of JLT from gamma. Just a standard definition. And the third derivability relation is as follows. First, consider A assumption leaf in A non-well-founded derivation. That is leaf which is not marked by an axiom of GLT. If there is an application of necessitation rule, in between the path connecting this leaf with the root, I call this assumption leaf boxed, and otherwise not boxed. I will write sigma dot comma gamma a turnstile a if there is non-well-founded derivation of a where all boxed assumption leaves are marked by some formulas from sigma, and all non-boxed assumption leaves are marked by some formulas from gamma. And this relation is a generalization of these two relations, that is the only non-trivial implication is this one. It essentially means that the Lindstrom probability logic is closed under non-well-founded proofs. I mean, if a formula is provable by a non-well-founded proof in this logic, then A is a theorem of this logic. Okay, and I will work with this generalized derivability relation.
I have a question. So
yes.
Your non-well-founded proof trees, the leaves may also have loops axioms at the leaves.
It's not essential because Lopes axioms can be obtained via non-well-founded proofs
the
from.
question was, why do we need them?
We can eliminate them, but in the context of non-well-founded derivations, it doesn't matter. We can just imagine that instead of Lopes axiom, there are some non-well-founded proofs of them.
Okay.
Yes.
But from the previous work of yours, my idea of the main purpose of non-well-founded proofs was to eliminate Lopes axioms.
Yes, but that work was on cyclic proofs, and if we
okay, here we are not in the cyclic context.
Yes, in the arbitrary non-well-founded proofs, yes, it doesn't. Let me just state that a formula is provable in the Gödel probability logic if and only if, let me say it like this, GL is K4 plus cyclic proofs. What I mean, a formula A is a theorem of GL if and only if it is provable by cyclic proof in K4. Yes, but if we now it doesn't matter.
Okay, we are interested in consequence relations from this infinite set of assumptions.
Yes. Now I define corresponding semantic consequence relations over GLT neighborhood frames. I will write that I call that A is a global consequent of gamma if for any model, GLT neighborhood model, if all formulas from gamma are true at all words of this model, that then A is true at all words. Global semantic consequence. A is a local semantic consequent if for any m and for any its world x, if all formulas from gamma are true at this point, at this node, then A is true. And the third relation, looks like this. I will write sigma dot comma gamma semantically entails A, that is for any model, for any its world, A is true at this world whenever all formulas from sigma are true at all words except x. We consider all words except x, and all formulas from sigma are true at these words. All formulas from gamma are true at x, then A is true at x. Yes, A is true at this word whenever all formulas from gamma are true at this world, and all formulas from sigma are true at all other words of our model M.
Its formulation may be.
Yes. Yes. Thank you. And the same, by conditions, the same equivalences hold. So this third semantic consequence relation is a generalization of these previous two relations. And global completeness means that
May I ask you something about this definition number 3?
yes.
So, if the idea is that sigma is some kind of boxed thing, what one would assume here to appear would be the condition that in some neighborhood, in some punctured neighborhood of x, sigma would hold. Then, and here we somehow quantify over all points in M.
Mm-hmm.
Is it really a difference, between these two?
If we define this consequence relation, semantic consequence relation like this, given sigma, gamma, A, and A is true at this word whenever all formulas from gamma are true at this word, and there is a punctured neighborhood of this point where all formulas from sigma are true, then we obtain an equivalent definition of this consequence relation.
Okay. Because it quantifies over all spaces M, and we can restrict it to this neighborhood or something like that? Or would we-
In such a formulation, we can immediately see that that this equivalence holds. That is, if formulas from gamma are true at every word, it literally means this thing. Okay. And in a simple version of global completeness theorem, the simple version can be stated as like this. A is derivable from sigma gamma if and only if A is a global semantic consequent of sigma gamma over GLT neighborhood frames. As consequences, we can obtain similar completeness results for local and global consequence relations. But further, I will work with specific GLT neighborhood frames. Given a GLT neighborhood frame, we see that its reduct is in a Sakia frame.
I think they use the term Sakia frame for something else related to inductionistic logic. The Sakia space and the Sakia frame.
A Sakia neighborhood frame.
Sakia space for Sakia duality. Yeah, there is such a term.
I would not move to this definition of.
Yes, I remember. Maybe I forgot something, but this term you used together with David Gabilai in some of your papers or reviews. Magari frame, and I guess in other paper Sakia frame for such a thing.
Okay, I'll check that because I'm not sure that.
Or maybe I
We can call it
was misled.
GL frame, right?
Yes, GL frame or Sakia frame or Magari frame in other terminology.
Sakia invented the term Magari algebra.
I guess the name Isaki is how to say.
Well deserved, but the only thing is that it should not clash with something else. But okay.
Yes.
Okay.
Isaki frame or jet frame, and it appears that we can obtain a GLT frame from any Isaki frame as follows. Let us define transfinite iterations of this mapping. I mean, given a Isaki frame, I will define iterations box alpha for all non-zero ordinals. And box alpha V, it's just the union of box beta V for all beta less than alpha, or maybe I should write box 0, just box 0 V just equals to V, and then this definition. Oop. Okay, and now we see that very simple observation that if X box is such a frame alpha infinite ordinal, then X box alpha is a GLT frame. Is a GLT frame. We shall only check these axioms. And normality axiom, but let me only check these ones. Box V is a subset of any iteration of box from this definition. Any iteration of box from transitivity, we have that any iteration of box is subset of box of this iteration. Since box V is a subset of box V. And finally, I forgot, this is by condition. Iteration of box equals to iteration of box where we add one box inside, and this is valid for infinite iterations. Let me skip further details, and in the sequel I will consider GLT frames of this form, where instead of the second mapping, for the second mapping we have omega-1 iteration of the first mapping. Omega-1 is the first uncountable ordinal. And
a small question on the Sakya frame is that understood the Sakya frame in this definition is merely complete atomic and completely multiplicative Magari algebra or not?
Here we have just complete atomic Magari algebra or spatial Magari algebra. It's not completely additive or
multiplicative.
Complete multiplicativity is not valid for arbitrary spatial Magari algebras. Okay. And I will write star. Will I consider only GLT models over such GLT frames. So I will prove this. There are two directions. Soundness means that if A is derivable, then A is semantically valid, is a semantic consequence of sigma gamma, and I will skip this direction and concentrate on the other part of this proof. And our plan is as follows. Suppose A is a semantic consequent of sigma gamma. First, we will show a kind of neighborhood compactness result and prove neighborhood compactness that we can put here gamma naught, a finite subset of gamma instead of gamma itself. And in this case, A is a consequent of sigma and a finite subset of gamma, gamma naught. The second step will be as follows. We define a sequent calculus for the Lindstrom probability logic with non-confounded proofs where sequence will look like this. Pi and delta are will be finite multi-sets of model formulas, and sigma will be an arbitrary set of formulas. Such a sequence is called valid if disjunction of all formulas from delta is a semantic consequent of sigma and pi. Thus, by definition, it means that sigma gamma naught A is a valid sequent. Then I defined this sequent calculus and show that any valid sequent is provable. Any valid sequent is provable in our sequent calculus S, and sigma gamma naught big arrow A is provable in S. And the final step
So valid sequence means that so this is more or less so it's from left to right. Is it not obvious by definition?
This arrow, yes, it's just by definition. So having this statement, we by definition see that this is a valid sequence. Then we prove that all valid sequences are provable in our sequent calculus. We obtain a non-well-founded proof of this sequence. And this non-well-founded proof can be transformed into Hilbert-style derivation. And that this is it's all of that. I just write like this. A is derivable from sigma gamma in a Hilbert-style, by Hilbert-style non-well-founded proof.
So this is also an easy step.
Yes, it's so it's an easy step. This step is by definition. So we have two main steps: this one and this one. How much time do I have?
We can negotiate. Normally speaking, 45 minutes.
Okay.
I think it's just enough to prove both terms.
I will show main constructions, but omit proofs. First, let me show you so-called ultra-bouquet construction introduced by Valentin Schechtman in order to obtain such neighborhood compactness results.
May I ask you, before we begin, a general question? So suppose we restrict our attention to spaces which are just ordinals with appropriate topology. Integral topology for box and iteration of it for this Lindstrom box. Would the same result hold? Would the relation, would the consequence relation star be equivalent?
So basically, is it complete with respect to ordinal?
Yeah, complete in this more general sense, in the sense of both global and local.
For the case of GL, we know that it is sufficient to consider only Isakia frames of this form. I mean, countable ordinals with interval topology. And it can be obtained like this. If we already know neighborhood completeness result, then if A is not derivable from sigma gamma, then there is a countermodel, a Isakia countermodel. And from such a model, we can extract ordinal. I draw it in a tree form. We can extract a quantum model over a countable ordinal with interval topology. I guess similar step could be done here. But yes, it's unwritten. It's
but it is likely.
by conjecture is like this, that for any if A is not derivable from sigma gamma, then there is countable ordinal lambda, such that for any countable alpha bigger than lambda, there is a countable ordinal beta, such that this beta with this alpha iteration of this mapping for interval topology of this beta already gives us quantum model, GLT neighborhood quantum model for this entailment.
This is hypothesis, right?
Yes, it's my conjecture. So I appreciate if someone will join me in this step. Okay. Yes. I'm going to show you ultra-bouquet construction, which gives us neighborhood compactness for Lindstrom probability logic. Okay. sigma gamma naught A. It's neighborhood compactness result, and yes. Yes. A subset of an Esaki frame is open, is called open subset V, if V is a subset of box V. Now suppose we have a countable sequence of Esaki frames. X. Together with closed points of these frames. Closed in this sense. It's complement, yes, its complement is open. Now let us define ultra, and we need also an ultra filter over N. Ultra filter over N. Now let us define ultra bouquet which is obtained as a set, as union, disjoint union of these axis frames by identifying all these points, x1, x2, x3, and we see kind of bouquet here. I use here algebraic language instead of topological, just I guess it's more shorter than topological. I just define box mapping on this disjoint union with identifying points x1, x2, etc. This box mapping is defined as follows. If we consider box V is any subset of this bouquet, then its restriction to any member is equals to box N and so we define all intersections of this box V with all members of these elements of this bouquet instead without this point. And X star obtained by identifying this sequence of X's belongs to box V if and only if and only if the set of such natural numbers n such that xn belongs to box n of the restriction of V to the nth member of this bouquet if all this set belongs to the ultrafilter. an important property of this definition that we can, if we any ultra bouquet of any Sakia frames is in a Sakia frame, and moreover, if we have an ultra bouquet of a Sakia frames, then similar conditions will hold if I write omega 1 iterations on all boxes here. I will write it. I will write it.
So for omega 1 iteration of box, similar conditions hold.
Given an ultra bouquet of Sakia frames, then we have similar conditions for all omega 1 iterations.
All alpha iterations.
On omega 1, not alpha. All alpha for only the first line, but only for omega 1 for the second line.
So why does it matter whether there's omega 1?
Essentially because we have only countably many members in this bouquet. Let me maybe show the second line for omega 1 iteration. Let us assume that we already know that alpha is bigger than 1 is equals to then let us show that x suppose x star belongs to omega 1 iteration of this box of V. By definition, it means that x star belongs to box alpha V for alpha is less than omega 1. Because box omega 1 is the union of all such stats. Okay, let us apply this equivalence. It means that the set xn now I write here box alpha V yes, just by this line. Now by transitivity not by transitivity, now from this line I can rewrite this set like this. I can rewrite it xn without small xn intersection of box box alpha v. Yes? Sorry.
Maybe we should use the third line.
No, this set I shall, otherwise it's incorrect. X and sorry. Now, yes, we shall use this.
That should be x minus xn.
We shall use this. This looks like this. And we shall write here box n alpha. So it is a subset of box n alpha xn minus x small xn. Yes? From this line. I write here subset.
Okay.
Subset. Xn belongs to this. And this means, by definition, that xn belongs to box omega 1 iteration of box n. Alpha is a countable ordinal. That is, xn belongs to omega 1 iteration of box n of this set. So this set belongs to our ultrafilter. Then this set also belongs to our ultrafilter. Okay. Other direction. Suppose this set belongs to ultrafilter U. Consider this set xi, I from this set, and we see that by definition x1 prime belongs to box alpha 1, not 1 but I1 iteration of this set. The second point of this set belongs to alpha 2 iteration, then alpha 3 iteration, alpha 4 iteration, etc. Yes, now let us put supremum of all this countable ordinal. It is a countable ordinal because we have only countably many members in this bouquet. We have such a set for alpha supremum of this alpha of the sequences of alphas supremum, and now we use supremum, that is, we have the set n xx n belongs to box n alpha, and something belongs to ultra filter. Then from this line, yes, we can now rewrite. I guess we can rewrite this set like this, then using that xn is closed, rewrite like this, then use this line and obtain here x star belongs to box alpha v, alpha iteration of box, and from this obtain, or what, like this, box alpha iteration of box, from this line and this line. So what does it mean? Suppose alpha is not a semantic consequent for any finite subset gamma naught of gamma. Then we have a series of quantum models and points in these quantum models, M1, M2, etc. Without loss of generality, we can assume that all these points are closed. It's another step of this construction. Then we put ultra bouquet and define evaluation at this point like this. This point x star belongs to value of a propositional variable p if and only if so using this ultra filter, we can extend our valuations from all this point to ultra bouquet. And it turns out that this model over this ultra bouquet gives us a quantum model for this statement. Here we see the connections which give us which tell us how box and omega iteration of box can be calculated in terms of mappings on members of this product. Let me move further. The same step. It's completely analogous to the case of the Gödel probability logic. Completely with this addition.
Compactness we prove by ultra-product construction.
Yes, but now we prove compactness not for all GLT frames, but for frames of our special form. And here we see that this omega 1 iteration somehow
Subsumes everything.
commutes with countable bouquets.
Mhm.
Okay, now I will we obtain apply neighborhood compactors. We obtain that sigma gamma naught entails A. Now I will write out rules of our sequence calculus. Pum pum pum. Yes. Gamma and delta are finite multisets of formulas here. Initial sequence, ordinary inference rules for implications on the left and on the right. If I erase these sigmas, then I obtain just standard sequence calculus rules for classical logic. And we have two model rules.
So in these rules, sigma doesn't play any role, right?
Yes. I forgot. Epsilon is written usually written like this. Epsilon. Okay. Sigma naught is a finite subset of sigma. Now we see here on the right part of this, from the dot comma, this finite subset of sigma. Okay, and the second model rule, there are variants for this rule, but now at this moment I will write it like here, the rule for introducing box times. Sigma naught, box gamma, box epsilon, box SA, where S is finite and is equal or greater than 1. In other words, here we have box A. Zero for the second model connective. Now let's try to show that all valid sequences are provable. The proof. A proof in the secant calculus is an arbitrary, possibly infinite tree of sequence constructed according to these rules, where all leaves are marked by initial sequence. Now let's try to show that all valid sequences are provable. Given a valid sequence sigma, gamma, delta, the first case that this valid segment can be one of these two initial, has the form of initial sequence. In this case, it's trivially provable. The other case, maybe there is an implication of the left part of this valid sequence. Then it turns out that both premises of this rule are also valid. So from a valid sequence of this kind, we can obtain two valid sequences of this kind. If we have a valid sequence of this form, then this premise of this rule is also valid. And now it remains to show that given valid sequence of this form where pi and delta do not contain implications, and gamma doesn't contain the falsity, then we can apply these rules bottom up and find valid premises for our valid sequence, such that our valid sequence can be obtained from a valid sequence by an application of one of these two inference rules. If we will show this, then given any valid sequence, we can construct non-well-founded proof of this sequence in S bottom up. Just bottom up. Because we will show that any valid sequence is either an initial sequence or can be obtained by one of these rules from a valid sequence. Now,
so this is a sequence of rules indexed by S, or is it one rule with many?
The only one. Here we have the only one premise.
Only one premise. Yes. So this is in fact a family of rules.
Like. So it's a schematic rule, but a little bit different from such schemes, from such rules. Okay.
Yes, so the bigger S, the stronger becomes the rule.
Yes, suppose we have valid sequence of this form without any implications in pi or delta, which is non-initial. Let box I1 box A n box times A prime, A1 prime, box A M prime are all boxed formulas from delta. We shall prove that there is a formula from this set such that sigma.com sigma AI, if this formula has this form, or and there is such S. If this formula has this formula. If we prove this claim, then immediately from compactness, we can write sigma naught here or here from these validities and write a big error, big implication here instead of this turnstile symbol and obtain valid premises, one of these two rules. So now we would like to show that there is a formula from this list such that if this formula looks like this, then this statement, assertion is valid, or if it looks like this, there's S such that this assertion is valid. Let us prove it by reductio ad absurdum. Suppose that for any AI we have AI is not a semantic consequent, and for any A prime and for any S bigger or equal than 1, this assertion does not hold. Then we have quantum models of our form for I Okay, it is the first series of our quantum models. And the second series, X, J, S, where S can be arbitrary large natural number. So there are many quantum models on the right. Okay, and corresponding evaluations. In order to obtain a quantum model of our form, I mean box and omega-1 iteration of box, we shall transform this series of quantum models. And in order to do this, I will show a lemma, a I will show you. Which will be familiar to those who know probability logic. Let me, sorry, another page. Yes. Suppose that we have the following semantic consequence. Suppose box S a finite natural number is greater or equal than 1. Box SF is a semantic consequence of sigma, box E, and some finite number of these reflections. Then we can erase these reflections but increase this number S. It resembles a situation when we prove that any Margaret algebra of infinite height
There's a point where
has a reflexive point. Suppose instead of box F I write here falsity. Just erase sigmas, or for simplicity erase box E. If finite number of reflection principles implies falsity, then already without assumptions we have box some finite iteration of box falsity, which contradicts infinite height of Margaret algebra. So it's a generalization of this statement.
I believe that GL canonical frame has a reflexive point under the similar circumstances.
Yes, but for GL, canonical frame is not an Esaki frame. Okay. Now let us consider this line. Box E is now conjunction of gamma and epsilon. And we see that sigma dot comma sigma together with box conjunction of gamma and epsilon does not imply box S A prime for all S bigger or equal than 1. By contraposition, if instead of F we write here A prime, we
This one is not provable.
Yes, is not a consequence for already for s round. Just s, put s equals to 1. Put s equals to yes, put s equals to 1. That is for any, instead of a, let us write a prime. Let us consider a contraposition. A prime. For all k, it's not provable. The statement is not valid. Then, for any finite number of reflections, box A prime is not a consequent of this set of hypotheses. By compactness, we immediately obtain that we have that sigma dot comma sigma with all reflections Otherwise, if a box A prime is a consequence, then by compactness there is a finite subset of this set such that we would have this assertion. Okay, so from any such countable series of quantum models, we can obtain this one quantum model with reflexive point in it. So instead of a family, let us write here Y1 quantum model where all formulas from sigma are true at all words. All these formulas are true at this point. Box A prime is not true at this point, but this point is reflexive for the first model connective. That is, for any D, box D implies D is true at this point. And analogously for all other families. Now I erase this lemma. Now let us grow tails in these models. I mean, consider a situation. Let us add a point here. I don't want to have. Let us like this, A1, 2 point. I will tell you very briefly. Every neighborhood, open neighborhood of this point must contain this point. Or algebraically, it means that A1 2 belongs to box V if and only if A11 belongs to V intersection box V. What is going on? Now let us evaluate all propositional variables at this point precisely like in this point. And one more observation we need is as follows. How omega-1 iterations behave here. And we have that this point belongs to omega-1 iteration if and only if y1, 1 belongs to omega-1 iteration. Why? Suppose this point belongs to omega-1 iteration, that it belongs to box alpha for countable alpha iteration. Then by this definition, A1, 1 belongs to box alpha for countable alpha, and by transitivity, A1 belongs to omega-1 iteration. Now, suppose y11 belongs to box 1 omega-1 iteration, then we can write here countable alpha, box alpha, box alpha, or box alpha, and here we can write box alpha plus 1 iteration. But alpha plus 1 is also countable. Then box omega-1 is here. So for our valuation, all formulas of the form box times h, any formula of this form is true at this world if and only if it is true at this world. And for all other formulas. Now let us grow these tails further up to omega-1. I mean, let us add y1, alpha for any countable alpha. And the final step, in order to obtain contour model for this valid sequence, let us add new point. Z. Yes, all the points here and all tails here.
So what you have just added is so this is a neighborhood on this point, right? So
yes.
If these were Kripke models, that would be rather familiar. So with these neighborhood models, they are somewhat.
Yes, any neighborhood of this Z looks like this. We consider neighborhoods of all these points and neighborhoods of these points together with all these tails and obtain a punctured neighborhood of this Z. All propositional variables from pi now we said that they are true at Z. All propositional variables from delta, we said that they are false at Z. All formulas from sigma are true at all words except Z, because here we already have these evaluations, and all these points of this tail coincide. So sigma, all formulas from sigma were true at all words here. Thus, all formulas from sigma are true at all points of this tail, at any tails. Pi. I already said that pi consists only of propositional variables. Box gamma. Gamma, box gamma. Yes. Here already gamma and box gamma, all these formulas are already true at all this point. Here, box gamma this formula were true, but now this word has all reflexive principles that gamma is true here and completely the same at all points at this tail. Box times epsilon. Box times epsilon, but we have that box times epsilon holds at every point here. That is box box alpha 1, box alpha 2, box alpha n epsilon hold at this point. There are finitely many points. We can see the supremum of these countable ordinals. Here, we already has simply box epsilon, not box times. From reflexivity, epsilon, box epsilon are true. So already the first iteration of box already give us a box epsilon here, and we obtain box times or box omega 1 epsilon at Z. Okay, now why all formulas from delta are not true, are false? Propositional variables trivially are false. The falsity is false. It remains to consider formulas of this form. Box A1 refuted at the A1 refuted at this point, etc. Now here we need to here we have conjunction omega 1 many conjunction of countable iterations of diamonds. I mean that it means that here okay. Box diamond. Box or diamond not A prime holds here. Diamond not A prime holds. Yes, I erased, but we obtain a model where box A prime is not hold. So diamond, here we have diamond not A prime. And here diamond, then diamond, etc. up to along all countable ordinals. At the point y1 omega, we have box n for all natural numbers, n not a prime,
Okay.
etc., etc. Yes. So this we have shown that any valid sequence can be obtained by one of these inference rules from valid sequence. Now, for any non-derivable, non-valid, non-derivable statement, a false statement of derivability, we have a quantum model of this kind, and a question which you addressed remains how to extract a countable ordinal with countable iteration from such a quantum model.
Do we have an example showing that less than omega 1 is not sufficient to get this result? Maybe it's written. Let me. You can call something like a descending sequence by countable many letters.
Yes. Maybe this will work. Consider the following set of assumptions. Given a countable ordinal alpha, gamma alpha consists of such formulas. Yes. Then let us consider frame alpha plus 1 box times where box B is defined from left topology, I guess. Is defined from yes, it's defined from left topology, and box times V equals to alpha plus 1 for any V. For any V. It's easy to show that X is a GLT frame. Let us consider neighborhood model over it where if and only if X is less than beta. So yes, P beta is true at this point if only if X is less than beta. We see that all these formulas are true at all worlds. At the same time, we have that yes, box times falsity, but E and we see that gamma A globally does not imply box times false, it implies P alpha. But for any GLT model of the form X box beta, where beta is less than alpha, this consequence, this assertion will hold. So if we restrict ourselves only by countable ordinals less than alpha. I guess. Pop. Yes, it seems that if we restrict, then for any such model, if all formulas from gamma alpha are true, then so we need all iterations. That is on this topic on Lindstrom probability logic, and thank you.